Welcome to our next lesson in biostatistics. This, just to set the stage a little bit, this is the beginning of what some people call a statistics parade. We will be looking at a variety of different statistical tests, and for each one of them, what I generally do is I talk a little bit about what that test does, what it looks like as a graph, some of the kind of important features of it, and then the second part of that is I show you how to run that test in SPSS. And embedded in that particular discussion is the concept of going through the different parts of the test, stating the null and alternate hypotheses, what are the assumptions, and all of those kinds of things. So this first part, we're really thinking about one of our new statistical tests. Specifically, we're looking at simple linear regression, and we will kind of go through that as a test itself, a statistical test, and then we'll talk later on in this lesson about how to run that in SPSS. So let's start off by looking at a scatter plot. You'll hear some people call it a scatter graph or a scatter diagram. They all really mean the same thing. In essence, what you have with a scatter plot is a collection of data points that are shown graphically on two different scales. And so this is a perfect example, and I'd like to kind of systematically go through this graph. This is how I look at a graph. First thing I do is I look at the title, and in this particular situation it says Figure 1, correlation between countries' annual per capita chocolate consumption. So that tells you a little bit something. It tells you not only are we doing a correlation, but what one of the variables is, and the number of Nobel laureates per 10 million population. So it tells you that you have two variables and you're looking at a correlation between them, which makes perfect sense if you're looking at a scatter plot. The correlation coefficient is something that we would be interested in for a scatter plot. So they also have a couple of pieces of information up here that we'll talk about a little later. But the next thing I look at is the x-axis. I want to know which one of those two variables that it listed in the title is the x-axis, and it says here chocolate consumption, kilograms per year per capita. So this is the annual per capita chocolate consumption. That's just another way of putting that. And then the third thing I do is I look at the y-axis. Here we have our Nobel laureates per 10 million population. And so this is a number, 1, 2, 3, 4, 5, 6, all the way up to, looks like somewhere around in the kind of mid-30s, roughly. And, well, that's a good point. On the x-axis, it looks like we have anywhere between 0 and 12-ish kilograms per person per year. So this must be one of those studies where we look and see how much is sold, probably, out of the grocery store. Here, then, the fourth step, and this I think is what a lot of people jump to at the beginning, is to look at the data points. We look at the data points, but we really aren't oriented to what's going on in the graph to begin with. And so now that I'm oriented to this scatter plot, I'm going to look at some of the data points. It looks like we have Poland and Greece and Australia. Here's the United States, Austria, Denmark, Norway, Switzerland, Sweden, UK, Ireland, and Germany. And if I were to do the 10-yard test or the 10-meter test and stand 10 meters away and look at this, probably the most obvious thing that I would see is it looks like there's kind of a cloud that goes this direction. I don't see much going on in this quadrant, top left. I don't see very much going on down here, bottom right. And so I kind of see this collection right here across the middle. And so I'm looking at the data points individually a little bit. I'm interested to see, oh, there's Canada, there's the United Kingdom, Ireland, and so forth. But then also sort of the general idea of that scatter plot. Not all scatter plots have a cloud that is distinct. Some of them are just all over the place. Some of them might have a cloud that goes down and to the right. So it might be pointed the other direction. This one clearly does not have that kind of a direction, but that's just kind of an orientation. Now we're going to be using this this scatter plot throughout our discussion of simple linear regression, so I'm glad we had an opportunity to look at that. So I'm scrolling, here we go. When I talk about a cloud, see, these data points are kind of like this cloud that I've been describing. That's why, hence the title, it's in the cloud. What we generally think of is the concept of correlation. And so even the title of this particular figure says correlation in it. When we have a scatter plot like this, generally we're interested in looking at correlation between those two variables, and so that's the language that we use. And so anytime you see a cloud, I want you to think of correlation. Now there are three main qualities of, quotes, the cloud. One of them are these data points, do they have tight or loose clumping around kind of like a general line? The second is whether that is a straight versus a curved line. Does it seem to be kind of like a ruler, or is it more like a noodle? And then thirdly, does it slope up versus does it slope down? So this is kind of like an upsloping line. So let's take a look at those one at a time, each of those different qualities. So let's start with sloping up versus sloping down. And so here would be an example on the left-hand side of a sloping up group of scatter points. Often your graph doesn't necessarily have the line going on it. You'll just see the data points. But if you, in general, it looks like that cloud is moving up and to the right, then that is a sloping up. If, on the other hand, it seems like it is going the other direction, top left to bottom right, so as we move from left to right, it is sloping down, then we would call that a slope down. The next concept is, do those data points clump tightly around that line, or do they clump loosely around the line? So I've given you kind of a couple of scenarios here. This is tighter. On the left-hand side, the data points are closer to the line. If we were to draw little lines to connect them, like invisible strings, those strings would be shorter. Here on the right-hand side, if we had a little invisible string to connect some of these dots, some of them are really far away from this green line. And so this is a little bit looser. The tightest clumping you'll see is if all the points fall exactly on the line, and the loosest that they can be is if they're just sort of randomly all over the place and there really isn't any pattern at all. And then the third thing to think about is whether this is a straight line versus a curved line. And sometimes this is a little bit difficult to tell. Sometimes it's more obvious than others. But the thing I'm looking for with a straight line is that there are data points all the way along on both sides of that imaginary line. If we were to draw a straight line over here on the right-hand side, there would be an obvious section right here that is missing data points. And so for that reason, a curved line really fits through the middle of this data cloud better over here on the right-hand side. For the remainder of everything that we're talking about when we're talking about simple linear regression, which is all of this lesson, we really are going to be focused on the straight line scenario. There are ways of doing things with curved lines, but we are not going to be touching on that. So this is really what we're after, and correlation is really about that as well. So let's go ahead and take a look at our table again. And here's our chocolate consumption and Nobel laureate, so same thing. I've gone ahead and drawn an imaginary line. I've used green to draw what I think kind of goes through the middle of that cloud the very best. And there are a couple things I want to point out about this line. I could have probably drawn it a tiny bit farther. What I don't want to do is I don't want to draw the line way past where my final data point is on either end. That's called extrapolation. That would mean that I'm going to assume that this line works over here as well, or way up here on this end. If people were to eat like 20 pounds of chocolate, I'm going to draw that line out here and assume that that's going to work at that high end as well. So a couple things here, that it does not extend beyond the data that I actually have. Then the second thing that I like to point out is that I like to kind of, at least in my mind, if not with a kind of a pencil, I like to kind of draw a little bit of a curve. This may look like a football or a flattened out pancake or a beach ball or whatever, around the majority of the data, because what that does is it helps me to really see that cloud. I could have drawn kind of almost a circle around it, kind of like a hot dog shape. But then what that also does is it allows me to see data points that really are kind of all by themselves, farther away, out away from the cloud. We call these outliers or extreme values sometimes. And so the bulk of the data, if we were to count up how many countries are represented here, I'd say the majority of them are contained inside of my red lines here, and there are a couple that are outside. So drawing the lines really helps draw attention to which ones kind of fit the general pattern and which ones seem to be a little bit more outside of the pattern. Okay, so let's talk a little bit more about the qualities of the cloud, and we can relate that to our table here. Anytime it slopes down and to the right, it's viewed from left to right. That's called a negative slope. Anytime it slopes up and to the right, that's called a positive slope. And so from now on, we're going to call this the sign of that particular correlation. So we want to know if it's sloping up or sloping down, and that is the sign. And so if we were to look at our table here, it slopes up and to the right, so this is a positive correlation. So we're looking at the correlation, it slopes up to the right, so that's positive. So we're looking at a positive correlation. The next thing about the qualities is, do they clump tightly or loosely around a line? And this is going to be the correlation number, the actual value of the correlation coefficient. And so we have both the sign of the correlation coefficient and the number that it corresponds to. And this correlation coefficient, sometimes it's called R, sometimes it's called effect size, or just Pearson correlation, or whatever. It ranges from -1 to +1. So remember how we talked about the sign here? The sloping down is negative and the sloping up is positive. If it's a -1, it slopes down and to the right. And this clumping around a line, if it's perfectly, all the points fall exactly on that line, or on our correlation line, then that would be a correlation of 1. Since it's down and to the right, it's a -1. Correlation of 0 is just sort of all over the place. There's no line that fits this data better than any other line. We could draw a line through this way or that way or straight across, and it's just a big ball of cloud. And so this would be considered a correlation of 0. A +1, we could put a plus mark here, but it's implied. A positive correlation, a +1, would be where all of the data points fall exactly on the line, and it is up and to the right, so it's a positive correlation, remember. So a perfect correlation of 1, the farther we get away from 0, means that those data points are getting closer and closer and closer and closer to the line. The farther those data points get away from the line, the closer we're getting to 0. And the slope then just tells us if it's a negative or a positive. So let's take a little look here at what would a correlation of 0.25 be. You can see that it's kind of like it's oval. It certainly is not round like we saw here. So it's round, but it's squished in one particular direction. So imagine kind of like flattening a beach ball. This would be the beach ball, totally inflated all the way as round as it could be. This is a little bit deflated, and we've managed to squish it so that it's maybe a little more like the shape of an American football. A correlation of 0.5 would be squished even more. The points are even closer and closer and closer to this line. A correlation of 0.75, those points are very close to the line. And then a correlation of 1 means that all of the data points fall exactly on the line, on a straight line. And so as you progress from a correlation of 0, positive 0.25, positive 0.5, positive 0.75, positive 1, those data points become closer and closer and closer to our imaginary regression line. And so this number, the correlation number that goes along with this, really represents how close the data points are to the line. Okay, so we have both the slope, the sign of that is either positive or negative, and then the number itself tells us how close those data points are to the line. And the whole idea of the straight versus curved line, this really is one of the assumptions of Pearson correlation. This is a correlation around a straight line. So how close are these data points to a straight line? If the relationship is curved, then that correlation coefficient that we're going to be getting will not accurately reflect the strength of that relationship. This is a strong curved association. See how those data points really fall very closely? And even though if we had a curved line to represent them, that could be closer to a 1, our correlation really is the same as if they're just kind of all spread out. And so we can only apply this to situations where a straight line through the cloud is the best fit for all of those data points, not where a curved line is a better fit. So this is called an assumption. In order for our test results to tell us the truth, then this assumption needs to be met. And so we have three things going on here. We have the sign of the correlation coefficient, we have the numeric value of the correlation coefficient, and then we have an assumption of the correlation coefficient. So those three qualities really then are helping us to know something a little bit more about that correlation coefficient. Okay, final page. So in summary, the correlation coefficient has a sign which tells us the direction up down of the slope, that numeric value, how close the dots are to the line. And I want you to burn that into your brain, because I think a lot of times people think that that numeric value means something else, and I'll go over what that is, but it's how close those dots are to the line. If they're all very close, then the correlation coefficient will be closer to 1 or negative 1. If the dots are spread out more, like a bigger cloud, like a partially inflated beach ball, then the numeric value of the correlation coefficient will be closer to 0. And that assumption is that we need to have something that's linear. So we have the assumption of linearity here. Now, I'd like to show you something that will help you to interpret what the actual number means. If you think along a continuum, we have, if we start at 0 to 0.1 really does not represent much of a correlation at all. Anywhere from 0.1 to about 0.3, this is a rule of thumb, so nothing hard and fast. Most people would think of that as being kind of a small effect or a weak effect, a weak correlation. Now the flip also works, because if it's a negative correlation, it just means that it's down and to the right instead of up and to the right. So anything between negative 0.1 and negative 0.3 would also be considered a small or a weak effect. So the complementary negative numbers work here too. From 0.3 to 0.5, we consider that sort of a medium or a moderate effect. And from 0.5 to 1, that's considered a pretty strong effect or a large effect. And so remember how when we were looking at our relationship here is the R for the relationship between chocolate and Nobel laureates. The R is 0.79, so pretty much if we rounded this, it would be 0.8. And so this is a good example of a pretty strong association, even with these outliers present. So this kind of gives you a good rule of thumb in terms of how to interpret those. A small effect might be something that kind of either partially or only for some people has an effect on that outcome. A large effect would be something that is more pronounced, it's a little bit more obvious. And so some people will say that we have found most of the large or strong effects. I'm not sure that we had ever looked at chocolate consumption and the number of Nobel laureates. And so you might be interested in looking at that paper overall. Their argument is that it's actually because of the compounds found in chocolate actually helps people to be smarter. And so there are a bunch of possible biases too that could be taking effect, but I would say that there are probably some large or strong effects that we have not yet discovered. And so that's kind of like a good rule of thumb. Now, some people will point out the fact that 0.3 is both small and medium, 0.5 is both medium and large. So I did not do this so that you would have a hard and fast rule. 0.1 to 0.29999 is small. As soon as you get to 0.3, then it's considered medium. These are just sort of ranges, kind of more of a gestalt kind of thing. If you read hundreds of papers, after a while you kind of get the feel for, well, that's kind of a small effect, or that's a pretty large effect. So these are not intended to be concrete or codified in any way. It just kind of gives you a general feel for relative to other kinds of things. In general, so basically the interpretation here is the farther we get from 0, the greater the effect. We can either be getting farther away from 0 in the negative direction or in the positive direction. Remember, our range is from -1 to +1. And so our correlation is anywhere in between there. Okay, so here is the caveat, and we'll be talking a little bit more about this in our next section of this lesson. The correlation coefficient does not tell us about the slope of the line, if it's a steeper slope or a flatter slope. The correlation coefficient tells us how close the dots are to the line, not how steep the line is. And so all three of these, I tried to draw them similarly. All three of these would have the same correlation coefficient because the dots have a similar distance from the regression line, the line of best fit. And so these three would all have the same correlation coefficient. It's not because it's steeper, it has a higher number. So do not get confused with that. The sign is the direction of the slope, up or down. The numeric value is how close the dots are to the line. And so if these dots are just as close as these dots are, then these would have the same correlation coefficient. So that concludes this lesson. Next, we'll be looking at some more pieces of simple linear regression.